All right, welcome to the hands-on piece. We are at the Google Collaboratory, and I've already pointed to the data source, which is called healthinsurance.csv. This is the data set we are going to work on. We begin by calling all the basic libraries like NumPy, Pandas, Matplotlib, and Seaborn, and suppressing the warnings because we don't like to see those unpleasant messages. Once these libraries have been loaded, we are calling the data frame through Pandas read CSV. This data set is about health insurance. So the background is that the insurance company that's a client, they already have some existing customers who purchased an auto insurance from them, which is essentially for their cars. Now this company is looking forward to pitch a health insurance to these people. So they already know these customers. They have relevant information related to these customers, but they're trying to pitch another product to them. We'll see what kind of features we have in this data. Let's first read the data. It's a small data set. We have about 10 features and 500 rows in this data. We've checked the shape. If we check the data types right now, we have a mix of data types. Majority of the features in this case are object type features, and there are two numerical features, age and income. Now, we can apply encoding only on the categorical variables, and we seem to have a plenty of these. Why? Because we will be trying all different types of encodings here on different variables. Please note your data frame doesn't have to have just one type of encoding. Different type of features demand different types of encoding. Let's just randomly sample 5 observations from the data overall, just to get a glimpse of how does the data look like. So if you see, these are the features that we have starting from gender, education, age, income, region, employment status, marital status, credit rating, car brand, because they already have an auto loan, and target column, which talks about whether this customer who already is an existing customer for the auto insurance has also subscribed or purchased a health insurance from this company or not. So in some cases, it's a yes, some cases it's a no. Now let's just glance through the features and understand their nature. Gender, what kind of feature it is, we can't have an order here. Education, you can imagine it would have an order. So it may have a sense of order. When somebody says this person has a master's level education, it's greater than the bachelor's level education, right? So you may want to bring a sense of order. Age and income are non-categorical variables. They're numerical, self-interpreted. Region, again, we may not necessarily want to assign an order unless we have a reason to believe so. Employment status, again, we don't know a specific order. Marital status, once again, we cannot give an order. Credit rating definitely comes with an order. When we say somebody has an excellent credit rating, that means it's better than the good. And that in turn is better than fair, right? So we have multiple options here. Car brand, there are different car brands that we see, and all these entries so far, at least in the 5 randomly sampled records, look different. So we may have more categories. Of course, we can't say there is a specific order here because we don't know how old that car is. An old luxury car might be at par with a brand new mid-range car in terms of pricing or insurance pricing. So we can't really build an order here. And the last column here is the target column. So we begin by working on the label encoder. We'll go in the same order in which we discussed it in the theory. Label encoder, as stated, will be applied only on the target column. So from sklearn, scikit-learn pre-processing, we are calling the label encoder class. It has to be instantiated like this. And then we are saying to the target column, do a fit transform, restore it back as the target column. So we are overriding the existing target column. If you see right now, it says yes and no. And when we do a fit transform of this label encoder on this, once again, when we check the head, what happens? It converts this into 0 and 1. Notice this is in alphabetical order. When we say yes and no, no alphabetically comes first. So that gets a 0, and yes comes later. So that gets a 1. That's how we encoded it. So target column is sorted. This is how these 2 categories would be identified. Now coming to the features which deserve one-hot encoding. And let's look at some of these features. Gender, region, employment status, marital status, and car brand. We are saying we don't have a sense of order here to begin with. Education has a sense of order, and credit rating has a sense of order. So we are not mixing these. We are trying to deal with those features which do not have a sense of order. And only those features are subjected to one-hot encoding. We are doing a small check here for all these features, which are supposedly nominal features, which means they don't have an order. We are saying we'll run a loop over them to look at the name of the feature and how many unique categories are present. For example, gender could have male, female, and others, or maybe just male and female. For example, employment status could have 4 or 5 different categories. So we are just checking how many unique categories are present, and we are doing a value count on that feature. So for I in nominal categorical variables, I would be each feature one at a time. Starting from gender to car brand, this loop is going to do that iteratively. And then finally leaving a space between what we print. So let's just check this. So you can see gender has 2 levels in our overall data. We have 267 males and 233 females. Region has 4 levels or 4 categories, and this is how the categories are distributed, so on and so forth. Everything else is okay. We have 2, 3, 4 categories, but the column called car brand here has 30 categories. And this is how the numbers are. So this is a synthetic data. It's not a real data. And that's why these numbers are very similar at places, but you get an idea. This is how we are supposed to work on such features. This has too many categories. Would this be the right candidate for one-hot encoding? Because one-hot encoding creates those many new columns. So if we have 30 categories, we'll create 30 minus 1, n minus 1 new columns, which is going to be 29 new columns on a data set which originally had only 10 features. Might not be very wise to do that. So let's deal with the rest of the columns first and see what we can do. And I'm going to show you two ways to do one-hot encoding. First is using the scikit-learn's one-hot encoder. The other is Pandas get dummies option. Let's do the one-hot encoder bit first, and then I'll show you get dummies. I personally would recommend that you try get dummies because it saves you certain lines of code. Let's make a copy of the data frame. So far, we have just handled the target column, which is through the label encoder. So we are making a copy of the data frame, and we are instantiating the one-hot encoder class. Now, when you apply one-hot encoder, the output that it generates is in the form of a sparse matrix. Sparse means it will have a lot of zeros. We don't want that. So we are setting that to false because when we do this, the output would be in the form of an array, NumPy array, which is very easy for us to handle. And then we are dropping one of the categories. This is being done just for that n minus 1 thing. So if you have n columns, we will be able to manage with just n minus 1 features as explained in the theory video. Let's take these columns, not the one which is car brand because it had 30 plus categories. We've taken the other 4 columns here that we are going to apply one-hot encoding to. So one-hot encoder, fit transform on what columns? These columns. So when I say df1 and the list of these features, it's going to select only these features from the overall data set. We are not changing the rest of the data. We are only selectively working on the columns that deserve this one-hot encoding. Finally, when you do a fit transform, like I said, the output would be in the form of an array, and we want to store it back as a data frame. So we are saying these will be our encoded columns, and we are giving it the names as per the original data. For that, we have something called as get feature names out. So this selectively shows the names of those features which are being subjected to encoding. This is the purpose of this entire input here. Finally, we will concatenate the encoded columns of data frame 1 to the original data frame, and the columns that were originally in the form of strings will have to be now dropped. We don't need both. If we have encoded it, we simply need to drop the original column. So this much effort needs to be put here. First, you select the features separately, you do encoding, then you concatenate, then you drop the original features. This much is the effort needed through one-hot encoder, and which is the reason why I said you may prefer get dummies, which is what I'm going to show you next. But let's run this now. And you can see gender column for that matter had 2 categories, male and female. Since we dropped one of the categories, we only left with male, and it'll have a 1 wherever the gender in the original data was male and 0 otherwise when it was a female. Region wise, we had 4 regions, north, east, west, south. One of the regions has been dropped and the remaining 3 regions are visible to us. So on and so forth for the employment column and the marital status column. This has created new features. So if we look at the shape of the data frame before encoding, that was df. If we check the shape of the data frame, just particularly the columns, we had 10 features to begin with. Now, if we check the shape of the data frame after one-hot encoding, that number would have increased. And that's something which we can check here by simply adding df1.shape1. Let's run this because we made a copy of the data frame, right? See, it has 14 features now. The number of features have gone up. Let's understand how do we come to this count of 14 now. Our original data frame had 10 features. How many new features will be added as a result of this one-hot encoding? N minus 1. So how many categories are there? 2. 2 minus 1 is going to be 1. How many new features will be added for result? It'll be 4 minus 1. That will be 3. How many new features for employment status? 3 minus 1. That is 2. How many new features for marital status? Again, 3 minus 1. That is 2 because we dropped the first category. So how many new columns we got in our data set? 10 plus 1 plus 3 plus 2 plus 2. If you check, that comes out to 18. But the output we saw was 14. Why? Because we dropped the original representation of all these 4 features. You also had a column which stated string-wise male, female, north, east, west, south. The original representation of these 4 columns, which have now been one-hot encoded, will again be dropped. So effectively what you have is 18 minus 4, that's 14. And that's the number of features that you can see here. Now, you saw this one-hot encoder and its application, 4 or 5 different steps involved. Why did I say it may not be the best choice? The reason for that is that there's a straightforward method in Pandas itself, which is called get dummies. And this is just one line of code. What you have to do is you have to point to the specific data frame. I'm working on the original data df only. You have to point it to the columns that you want one-hot encoding to be applied to, and you do drop first is equal to 2. So in this one line of code, you're pretty much making those changes in place rather than taking the data separately, applying one autoencoder, concatenating it back, and then dropping the features manually. If this saves time for you, it's your preference. You can apply one autoencoding directly like this. You have gender column as male, you have region column with 3 categories, employment column with 2 categories, and marital status again with 2 categories, n-1. The same thing applied in a straightforward way. Notice earlier when I did this, I created a copy of the data frame where I applied it through one autoencoder. Because I preferred this approach, I'm working directly on the original data frame here. And once again, if you check the shape of the outcome, it has 14 features. We started with 10 and now we have 14 features. Now remember, there was a column called car brand, which had too many levels, 30 levels to be precise. We could not apply one hot encoding there, fearing that it'll add too many columns, 29 columns, n-1. Can we do something about it? So I'm just showing you a treatment for that, and I'll show you an alternative way as well. Let's make a copy of the data frame at this stage. So right now we have 14 columns. That's our data frame. So just making a copy of the data frame at the current stage. We are looking at a count plot where we'll be looking at the car brand column of the data frame 2, which is a copy, and we'll be sorting the bars that we get in the count plot in a descending order of counts. Applying a rotation on the x-axis so that we can read the x-axis labels properly. When you have too many elements written on x-axis, there would be a clutter. Finally, we are calculating the value counts, which means for each car, how many occurrences are there. So we are capturing it as an object called frequency. Let's run this. This is nothing but the output of value counts. In a way, we saw this here earlier, and we are looking at it graphically now. So there are some cars which have occurrences like they occur 40 times, 30 times, 20 times, and some cars have just 2 or 3 occurrences. We are looking at the same information through this plot. And this rotation of 90 degrees essentially makes sure that we are able to read these labels here. Otherwise, these would be horizontal by default and will not be easy to read. Now, what we are saying is that if there are certain categories of cars which are very limited in occurrences, why don't we club them into one? That would lead to a reduction in the number of overall categories present in the column. And we'll be able to focus on the categories which are more frequent, more popular, you can say. That's what we are trying to do. So in order to do this, we are saying we will only consider those cars which are occurring more than 25 times, which means anything that occurs less than 25 times, let's club it into one category. The less frequent cars will be clubbed into one category called others. So we've decided a threshold, which is a minimum threshold. And we are saying from this output of frequency, which is nothing but the value counts, we are filtering those categories which occur less than 25 times or the threshold times, and we are capturing their names. Dot index means their names. If you do just this much without index, it'll give you a filter on the value counts itself. When you do dot index on that, it'll give you the names of those categories, car brands, which occur less than 25 times. And finally, we are saying that in the car brand column, let's apply a dot replace method where we will keep those features which are to be clubbed, which have limited occurrences, essentially less than 25 times, and we'll replace them with other. And then we are checking how many unique labels or car brands we are left with now. So remember, we had this number as 30 earlier. When we run this code, what are we left with? 11 only. So that number 30 categories have been reduced to 11 categories. And now if you do a count plot of this, you'll see others as one category, which has too many other categories clubbed into it, but the original categories of important cars are visible. And others is something, while it may be a high count, you can still discard because these are not those frequent cars. These are the cars which are relatively less common. Now on this data frame 2, where we perform this change, we are applying get dummies as we did earlier. So what has happened? We had 14 features when we came to this stage. We will drop the original feature, which is the car brand in the earlier representation. And we got these 11 new features for the 11 brands that we have, including others, and 11-1, in fact, because we get n-1 new column. So if you look at it effectively, 14 plus 11-1, that'll make it 24. And if you drop the original feature, that number will be 23. Let's see if that's what we get. And here you see this number is 23. We have 23 features in our data set now. 10 new features have just been added owing to this representation of car brand. So generally the rule of thumb is if you have a categorical variable with more than 15 or in certain cases 20 categories, you do not prefer one hot encoding. Again, it depends on the size of data, but the common threshold that people follow in practice is if a categorical variable has more than 20 levels or 15 levels in some cases, they do not prefer applying one hot encoding straight away. They try to club some categories, which is what we've shown you here. If you want to check how our features are now, we can check just df2.columns. You can see these 10 new columns here have been added through the variable called card brand. Get Dummies smartly shows you the names that the original card brand feature had a category called Ford, and that appears here. Had a category called Honda, that appears here, so on and so forth. So this is one smart way of dealing with those categorical variables which have high cardinality, which have too many categories in them. Now let's move to ordinal encoding. Now in ordinal encoding, we want to get a sense of order. Let's talk about the variable called education. We had a variable called education, which had 4 levels of education: high school, bachelor's, master's, and PhDs. We want to apply ordinal encoding. So we have an ordinal encoder that's available in scikit-learn preprocessing. We are calling that. And this needs to be told in what order you want to put your categories. So this is not a random order. Give it from the smallest to the highest order that you want to give. High school would be the lowest, and PhD in our case would be the highest. This input needs to be given by us in the right order. That's what we've done. And then finally, we are doing a fit transform on which column? The education column of the data frame. We are storing it as DF encoded. And we are just checking for the time being the original column and the encoded column, first few observations, to see how does it look like. So if you see, if we give the order, this would get 0, this would get 1, this would get 2, and this would get 3. Is that what we have? So masters would have got a 2. High school would have got a 0. PhD is the highest category out of 4. So that'll get an index of 3. Bachelor's is the second after high school. So that gets a 1. This is how the order. Now that you've got it, you can always drop the original education column from the data frame because we have got a numeric representation for it. This is when you have used an ordinal encoder from scikit-learn, which essentially goes in a sequence as you supply, starting from the index 0 to the highest level. But what if we wanted to give a specific weightage? And for that, we've reserved a variable called credit rating in our data. Let's say we want to say that excellent needs to be given a rating or weightage of 10, good needs to be given a weightage of 7, fair needs to be given a weightage of 3, and poor needs to be given a weightage of 1. Now, this is not 0, 1, 2, and 3. We want a custom order because we may have some intelligence around it, and we want it to be seen like that. Excellent has to be many-fold more compared to, say, a fair. We just don't want to give a difference of 2 between them. So now, custom encoding is not something that we are applying through a library. We are simply taking the credit rating column and using a dot replace along with this dictionary. If you see, this custom encoding that we have defined is a dictionary structure. Key is the label as it appears in your original data, and this value here is as you want to represent it. So we just apply this dot replace method. It understands that wherever I encounter excellent, I have to replace that with a 10. Wherever I find good, I will have to change it to 7. That's it. And then we can quickly compare the original credit ratings with the credit ratings as encoded. Let's do this. So as you can see, poor got a 1, excellent got a 10 because that's how we defined it. We have a label called good here, which has got a 7 here. Fair has got a 3, so on and so forth. This is how the ratings have been mapped. And once we've done that, we can drop this original credit rating column because we already got a custom representation for it. So this takes care of the custom encoding for us. Notice that we can also use custom encoding depending on our labels as we want to define them in place of ordinal encoding. We can just bring the right order and apply it. If you want to use it through scikit-learn library, however, you can do it that way. Now moving on to the last type of encoding, which is the target encoding. Remember, we talked about a blended kind of a probability calculation being done here based on the means and stuff. This is not straight away available through the scikit-learn library. In fact, it's there in a way, but it has a few glitches at the time when I'm recording this video. So I'm not using it from the scikit-learn library. If it gets resolved, maybe I'll create a separate video. But for now, we'll use it from the category encoders module. It's something that needs to be installed. It doesn't come there by default. So we'll have to install this, and then we can apply the category encoders. By the way, category encoders is a pretty rich library. It has at least 14 or 15 different types of encodings, but we don't necessarily need them all. So I'm just sticking to target encoding. Once this is done is when we can import the category encoders as C, just like we call NumPy as NP and so on and so forth. Within category encoders, we have a module called target encoder. That's what we need. And where do we want to apply target encoder? We want to apply this to the card brand column. Generally, you want to apply target encoder for features which have high cardinality. So I showed you an alternative earlier, which was reduce the categories, club them into others, and then solve it. The other way, or maybe at times a better way, would be a target encoder. So we are applying this to the column called card brand, and we are doing a fit transform, and we need to give it the input as the data frame and the target column in particular. So this needs to be told that this is the target column. We've already told the column with respect to which we are applying it, but it also needs to be told where is our target column. And then we can simply go ahead and rename the original card brand column with the card brand encoded. This is just to override the actual representation. Once we run this, you can see that there is a car brand encoded, which comes in these kind of numbers. And the original car brand has gone. So now if you see, looks like all the features are in the numerical representation. Remember, in the original data, we just had 2 features as integers and everything else was object. Let's see how is it now. So now you see original features, there were 2 integer features which are still there, but so many other features that we see are present here. So these are all numerical. These are floats, ints, and unsigned int, which is a little memory efficient way of assigning the integer representation to values which lie between 0 to 255. You can read more about this, but these have all been converted into numbers now. That's about the encoding. At this stage, your data would be pretty much ready to be given as an input to the model. Please note, there's one more aspect related to the train test split and all, but we've not touched upon it till now, and that's why I've not mentioned it here. That may be meaningful for people who already have experienced some amount of practical implementation of supervised learning. But for us right now, just understand the types of encoding which are applicable and when to apply what type of encoding. When we move to the supervised learning hands-on, we'll talk more about the way to practically apply them after doing a train test split and other stuff. There are also a couple of convenient ways of applying encoding through scikit-learn library itself using column transformer. But the limitation there is that all the types of encoding that you're applying should be from scikit-learn library. Now here, if you see, we've applied a mixed type of encodings. We've used get dummies from pandas, we've used scikit-learn, and we've also used category encoders last. So column transformer here from scikit-learn may not be necessarily applicable for us. We'll discuss these things as we get on to solve more advanced problems. Thank you for your time.